Alright, here's today's hard daily integral problem. The Daily Integral, if you're not familiar, is a website that posts daily integral problems every day. They post an easy, a medium, and a hard difficulty problem, and this is today's hard problem. And it looks like quite a mess. We have the natural log of an inverse, or I guess 1 over a main trig function, a secant theta. And then we have a tangent theta and a secant theta raised to an irrational power, which looks just quite the mess. But I will say that this integral is absolutely beautiful and collapses to a very clean result. And I think that's just what makes math so beautiful, is that something that looks this tangled and this complex can be something so simple. But without further ado, why don't we flesh out what that simple result actually is and get into this integral. Now, the first thing I'm going to focus on is this term up here. Sure, I guess that became an underline now. So this exponent here, it just looks like a mess, and I think we should take the time to simplify it, and we might get something cleaner out of it. So I'm going to rewrite it down here in blue. Negative 2 pi to the 1/3 over 2 to the 5/3. Now, what do we notice? Well, there's a 2 on the top and the bottom. This 2 on the top is 2 to the 1st, and the top on the bottom is 2 to the 5/3. So we can subtract those exponents because we're dividing. So 1 minus 5/3, that's negative 2/3 pi to the 1/3. Now, I do notice something here. I want to get the exponents the same. And one way I can do that is making this 2 to the negative 2, whole thing raised to the 1/3. Now you can see that that's equivalent, because if we do go and expand this again and multiply those exponents, we're just going to get 2 to the negative 2/3, which is exactly what we have over here. And now 2 to the negative 2 is 1 over 2 squared, which is 1 over 4. Of course, these exponents are the same here, so I can multiply the pi and the 1/4, and I simply get negative pi over 4 to the 1/3. That is it. That is that exponent right there, and I can go and plug that back into our integral, and we're already looking just a little bit better than we were before. There you go. That is our new integral now, rewritten with this new exponent here. Now we kind of get into the integration part of it. So the first thing that I looked for when solving this was a good substitution to use. I noticed that we have secant theta in the natural log, secant theta over here, and then just this tangent theta is kind of out of place. And so my first instinct was to try and get rid of that. Now, for those of you who are savvy with your derivatives, you'll know that the derivative of secant theta is secant theta tangent theta. So if I can make that substitution and get this tangent theta, I might be able to cancel them out. And so that was my first instinct there, and I landed on differentiating the natural log, just because if I can let the natural log be some term u, or rather the entire square root of the natural log, that term can collapse and fall out of there, and then hopefully the derivative of that natural log term cancels out some other things, and I'll be left with a much nicer integral. And so that was what I chose to do. U equals the square root natural log of secant theta. So du is going to equal, well, the square root, remember the derivative of square root of x is 1 over 2 root x. So this is no different. It's going to be 1 over 2 root ln secant theta, which that's just u. So 1 over 2u. And then the derivative of the inside now, natural log of secant theta, it's 1 over secant theta, and then times the derivative of secant theta, which is just right up top, secant theta tangent theta d theta. And the secant thetas cancel, and we are left with tangent theta over 2u as our derivative. Now I can work with that. So I'm going to just rewrite this so we can solve for d theta, because we're going to be subbing back in for d theta. So d theta equals, and then it's just going to be du times the reciprocal of that, which is 2u over tangent theta du. Perfect. Now, we also need to compute some bounds, right? So I'll draw a line here and we can compute our new bounds. So our bottom bound was for theta equals 0. Well, what is u going to equal when theta is 0? The square root of the natural log of secant of 0. Secant of 0 is 1 over cosine of 0. That whole term is 1. So we're really looking at the square root of the natural log of 1. The natural log of 1 is also 0. Square root of 0 is 0. So our bottom bound is still going to be 0. And our top bound, pi over 2. So root natural log of secant of pi over 2, which is 1 over cosine of pi over 2. Cosine of pi over 2 is 0. So we have the square root natural log of 1 over 0. Now 1 over 0 is going to approach positive infinity. And the natural log of positive infinity, if we think of the graph of natural log, which that's not very pretty, but still, it's going to be approaching positive infinity for larger and larger values of the input as well. So this natural log term is also going to approach infinity. Square root of infinity doesn't really change that at all. We're still going to make our top bound positive infinity. So we're going from 0 to infinity now in our integral. Let's rewrite it. So our new integral is going to be from 0 to infinity. This natural log term, the square root natural log term, is going to just be u, which looks so much nicer. Tangent theta, secant theta to the negative pi over 4 to the 1/3. And then instead of d theta, of course, we're going to have 2u over tangent theta times du, just making that substitution as well. So 2u over tangent theta times du. And of course, our tangent thetas are going to cancel, which is exactly what I wanted to happen. And we're just left with integral from 0 to infinity. Now we have a u, we also have a 2u being multiplied, so that's going to be 2u squared. I actually am going to bring that 2 out front as well. This 2 I'm just going to bring out front. So 2 integral u times u is u squared secant theta to negative pi over 4 to the 1/3. It's looking cleaner, admittedly, than this, but still not very good. We have a secant theta raised to a still irrational power. What are we going to do here? The real thing we're going to do here is solve for secant theta in terms of u. Now, how are we going to do that? Well, let's rewrite what u was equal to. And see if we can solve for what secant theta should be. So I'm going to square both sides to get rid of the root. Natural log secant theta. And I'm also going to raise both sides to, or I'm going to exponentiate both sides, sorry. So that becomes e to the u squared. It's just equal to secant theta. Let's go and plug this back into our integral. 0 to infinity. Oh, I almost forgot the 2. Of u squared. Secant theta is now e to the u squared. And I'm also, you know what? I'm going to move this down real quick and make another, not really substitution, but just notational shorthand. I'm going to let this value c denote our pi over 4 to the 1/3. Again, not a substitution. It's really just a notational shorthand for this pi over 2 or pi over 4 to the 1/3 term. But it's going to make this integral look so much nicer to look at, because that term is a mess. But that is what this comes out to. And we have our du. And I can actually simplify that a little bit further. 0 to infinity of u squared, and then these exponents can multiply e to the negative cu squared du. And so by the end of our entire substitution, we're left with this integral here. Now, this is the integral that we're going to be trying to tackle throughout this problem. So how do we really go about doing this? Well, before anything, I'm going to introduce something called the Gaussian integral. And this is going to be crucial to solving this problem. So this is the Gaussian integral. It's the integral from negative infinity to infinity of e to the negative x squared dx. Now, the shocking thing about this integral is that its result is just the square root of pi, which just looks like it comes out of left field here. I mean, we have some exponential that we're integrating and we're getting pi out of it. But this integral is actually far more important than I might be giving it credit for right now. So I'm going to draw out e to the negative x squared. I'll draw them at line x equals 0 here as well. So the area underneath this curve, which I guess I can do in yellow, that is just the square root of pi. Now, why is this function important? Why have we calculated this? How have we calculated this? I'm not going to go into how we've calculated it in this video, but there are plenty of online demonstrations of how this integral can be computed here. It's really important in statistics. This e to the negative x squared function is related to the normal distribution, or the bell curve. And so we need to be able to find the area under that bell curve, because the area under any probability function has to be 1. Not specifically e to the negative x squared, but the normal distribution, which is a scaled version of e to the negative x squared. So when you do go to integrate this, you need it to come out to 1. So that's sort of the reason why this integral is so important. As for the result, I think it's absolutely amazing that it comes out to the square root of pi, but again, we won't get too far into that. One of the things I do want to talk about, though, which we're going to use for the rest of the problem, is trying to fit our integral here to this form. Now, you can already see this e to the negative cu squared here, and yes, that's going to be quite important. But our bounds are different. Notice we have a negative infinity to infinity on the definition of the Gaussian integral, but only a 0 to infinity on our integral up here. So how are we really going to make use of that? Well, it has to do with something called even functions. An even function is a function where f of x is equal to f of negative x. For all x, you pick some x value of the function out here. This is x. And then if you go to negative x, well, the output is still the same. And that is true for e to the negative x squared. It's actually really easy to see why as well. You have e to the negative x squared, that's just equal to e to the negative. And if you plug in negative x for x, well, of course these are the same, right? You square negative x, you just get x squared again. The negative times the negative just makes it positive again. So, yeah, e to the negative x squared is an even function. Now, what that also means is that it's symmetrical about the y-axis here, right? If I take some output at negative x, it's equal to the same output when you go to x, right? And so what that geometrically also means is that the areas are symmetric about the y-axis too, right? This area over to the left is equal to this area over to the right. And so what that means is that if I wanted to write our integral, if I wanted to rewrite this big giant Gaussian integral here, well, if I go from negative infinity to positive infinity on this function over here, if I go from negative infinity to positive infinity, that's just 2 times if I went from 0 to infinity, just by the symmetry of that. That's still equal to the square root of pi. So that's sort of the geometric consequence for that. Now our bounds are the same, though. And if we just move this 2 over here, we can see that the integral we're actually looking for, right, this integral here, it's just the square root of pi over 2. And so we're going to be using that identity a good bit. But that is just a brief bit on the Gaussian integral there. And that's how we're going to continue this problem and orient ourselves for our solution. Alright, so I've rewritten our integral on the next page here, and it looks quite confusing, but now that we have the knowledge of the Gaussian integral, I'm going to use that to our advantage using an integration procedure called integration by parts. Now, I'm sure many of you have heard of integration by parts. It is quite a common, procedure in integration and in calculus in general. And it says that the integral of two functions, u times the derivative of another function, v, is just equal to the product of u and v minus the integral of v times the derivative of u. Now, u and v are both just functions of some variable here. If you want to understand why integration by parts is true, it's really just manipulating the product rule in differentiation, and then you can integrate both sides and figure out where this property comes from, and I can actually show that real quick. So if I wanted to take, let's say they were both functions of x, u, and v. If I wanted to differentiate u times v, it's obviously u prime v plus v prime u. That's just the product rule. Subtract both sides, this from both sides, and then if I integrate both sides with respect to x, well, the integral of the derivative of uv is just uv, and then minus the integral of v u prime equals the integral of u v prime. And that's literally our by parts formula. V prime is dv notationally, and u prime is du notationally. And so that's sort of where it comes from, just working through the product rule. But enough about integration by parts. How do we actually use it? Well, one thing we have to notice is that when we do go to assign one of these functions up here to be u, we're going to need to take its derivative, and that derivative is going to be in an integral. And we're also going to need to integrate one part, right? We're going to need to assign some function as dv, and then integrate it back to v to use this. I'm going to make some substitutions for the functions u and the functions v. What are these going to be? Well, one thing we have to notice is that, of course, we're going to be integrating v in our problem. Integrating v in our problem. And with this exponential up here, it's going to be kind of weird to do that. So we're going to need to be smart with our substitutions here. Now, the one thing that I noticed was that this integrand here, I'll rewrite the integral up here, can be written as u times u e to the negative cu squared times du. And this is what's going to be really important for us, because this term, of course, can be differentiated. It's u, it goes to 1. But this term here can be integrated now, because if we make a substitution for u squared, that thing's derivative, the derivative of u squared being 2u, is going to cancel this leading term out front, and we'll be able to integrate like normal. So this is sort of how you're going to have to break up the terms here, but this can be our dv, and this can be our u, and that is how we'll apply by parts. So, of course, u equals u, which looks really weird. This u in black is the u in our by parts formula that we need to substitute for, and then the pink u is the u that we're just pulling from our integral. Du equals du as well, and then dv is going to be u e to the negative cu squared du. And what is the integral of that? Well, why don't we write it out? So I can write it out over here. Integral of u e to the negative cu squared du. Well, we can let, we can let t equal cu squared. And so we can get from that, I'll actually write the substitution in blue just for consistency's sake. T equals cu squared. So dt equals 2cu du. Cool. And again, there are no bounds. This is an indefinite integral. We need a function. So we're going to have u e to the negative t. And actually, I could have just let t equal negative cu squared. I'm not really sure why I did that, but yeah, you know what, I'll do that real quick. I don't know why I left the negative sign out. If we keep the negative sign in there, then this derivative over here is just going to be negative. No big problem. Yeah, not really sure why I did that. But yeah, we have an e to the t. And then du is going to be dt, and divided by negative 2cu. And these u's, of course, cancel. This is why I picked this as our dv. And it simply becomes, I'm going to bring this negative 1 over 2c out front. Negative 1 over 2c integral of e to the t dt, which is simply negative 1 over 2c e to the t. And if we want to plug back in what t was, which is negative cu squared, it is negative 1 over 2c e to the negative cu squared. Ooh, there you go. Spanning the entire line there, but we got it in. All right. And I'm sure some of you could have done this in your head, working backwards, but I just wanted to flesh out the entire solution just for clarity's sake. But yeah, now we know that v is going to be equal to negative 1 over 2c e to the negative cu squared. Perfect. All right, so now let's go apply our integration by parts formula. So I equals, I just being this integral here, of course, that's what we've been trying to solve this entire time. And one thing that's important to notice is that our by parts formula is working to integrate this, right? However, there's still a constant of 2 out front, and we cannot forget about that constant of 2. So I'm going to actually multiply our entire integration by parts thing by 2. I'm going to bring that 2 down, just so we don't forget about it. And it's going to be 2 times this, which is how we integrate using by parts. Now, uv is going to be u, right, times negative 1 over 2c e to the negative cu squared. So u times v is going to be negative u over 2c e to the negative cu squared minus the integral from 0 to infinity. Now our bounds are back when we do by parts. But this integral is going to be a v times du. So this is our v, and that's our du, of course. And those two signs as well cancel, right? I can bring this whole negative 1 over 2c term out front of our integral. And so the negative and negative make a plus, and then the 1 over 2c is just brought out front. So I'm going to do that real quick. This term here needs to be evaluated on the appropriate bounds as well. We've implicitly integrated this part when I proved the by parts formula. You remember me integrating both sides. We have integrated that uv. It is the integral of a derivative, but we still need to evaluate it across our bounds. And so I'll logically break up this integral then into this first term I1, which I will denote as this, and then a second term I2, which I will denote as our integral here, right? Oops. And we can just say, just by looking at it, that I is equal to I1 plus I2, right? Oh, sorry, I should say 2 times I1 plus I2. Cannot remember that, or cannot forget that too. That's very important to remember. Perfect. There we go. And now we can just break it down part by part. So let's solve for I1 first. Now I1 is just going to be this negative u over 2c e to the negative cu squared term evaluated on the bounds. The e to the negative cu squared though, right? We have a negative exponent. I can bring it down into the denominator, and it's going to make it a little bit easier for me to see what's going on when we do evaluate at these bounds. Now, when we do plug in infinity, it's more like saying we have the limit as, that top bound b goes to infinity of this evaluated at b. Otherwise, we would be plugging in infinity, which is not a mathematically rigorous thing to do at all. You could still conceptually get the same answer, and it can be valuable to do that sometimes, but this is more so the proper way to write it out. We have some bound b that's going to infinity that we've plugged in. It isn't quite infinity, because infinity is not a number that's really defined. It is more of a concept, and it's approaching infinity. And then we're going to subtract off this evaluated at the bottom bound, which is negative 0, for 2c e to the 0 squared. Now, how do we evaluate this? Well, this first term, right, is going to be the trickier term to evaluate. As b goes to infinity, this top term grows linearly, right? It's just b. Originally, it was just u. It was a linear equation. It'll approach infinity. But the bottom, e to the c squared, is an exponential that's going to be growing very fast, a lot faster than the top. And so as b does get larger and larger, this entire term does actually go to 0. And the second term here, e to the c 0 squared, is just 1. And 2c times 1 is just 2c, so the denominator is just 2c. The top, however, is 0. 0 over 2c is again going to be 0. And so this entire term, I1, is just going to be equal to 0. So now we can plug that back in. And we'll get that I is just 2 times 0 plus I2, right? I1 was just 0. Oh, so really the integral that we're solving then is 2 times I2. I guess I can write this in red again. 2 times I2. And I guess I can write it in red because it's the scarier part. Which really isn't that bad. We're just going to have to fit that Gaussian integral to it, and things will clean up quite nicely. So let me bring down this I2 term. 1 over 2c integral from 0 to infinity of e to the negative cu squared du. Right? That's just up here, bringing that part down. Now, again, this looks exactly like our Gaussian integral, with the exception of that c being in the exponent, but we can work with that. I'm going to do a little substitution here. So this exponent here, the cu squared, it is equivalent to the square root of c times u squared, right? The c squared, root c squared is just c, and the u squared is of course u squared. And I need that to fit the form of you know, an x squared or some variable squared, right? Because e to the negative x squared dx, that's how this integral is written out, right? And again, this is going to be square root of pi over 2 for our given bounds. That was something we went over earlier in the video, but this is sort of the identity that we're going to be using. And so I'm just going to take the square root of both sides of this, and I can see that the substitution I need to make is just letting root c times u equal x. And I'm going to rewrite this in blue as well. Root c du is going to go to dx. Now, what are our new bounds? Well, if we plug in 0 for u, then that whole side is just going to go to 0, right? And x is still going to be 0. So the bottom bound is still 0. The top bound, if I plug in infinity for u, well, root c times infinity, that's just still going to go to infinity. So our bounds are actually the same. So when I come down to rewrite this, our bounds are going to be the exact same. E to the negative x squared du goes to dx over root c, which I'm going to write as c to the 1/2. And that's our new integral. It's a lot nicer, and I'm going to draw an equal sign over here because we can simplify this a bit further. I'm going to bring the c to the 1/2 out front. This is c to the first. This is c to the 1/2. 1 plus 1/2 is 3/2. Integral from 0 to infinity of e to the negative x squared dx. And again, this is our Gaussian integral from earlier. It's just the square root of pi over 2, which we can write as the square root of pi over 4. It's just the square root of pi all over 4. And now, when we go to plug this back in for what I is equal to 2 times 1 over 2 c to the 3 over 2 times the square root of pi over 4, which is just going to equal c to the negative 3 over 2. I'm just bringing this c up to the numerator, this one over here. The 2's cancel, of course, and times the square root of pi over 4. And that is all we need to evaluate now. So I'm going to plug back in what our c value was. Now recall that earlier in the video, I just said that c would be that pi over 4 to the 1/3 term that we had. This is pi over 4 to the 1/3, and then this whole thing raised to the negative 3/2. And then the second term, I'm going to also put an exponential, or right with its exponent. So the square root of pi over 4 is just pi over 4 to the 1/2. And some of you may have already seen where this is going. These two exponents here can do some simplifying. 1/3 times negative 3 over 2 is just negative 1 over 2. Pi over 4 to negative 1 over 2 times pi over 4 to the 1 over 2. And if you look at that, we have the same base. We can add those exponents. Negative 1/2 plus 1/2 is just 0. And so we get that pi over 4 to the 0, anything to the 0, is just 1. And so this entire integral that we've been solving this entire time is simply equal to 1. I thought this was a pretty cool result. I cannot believe that that square root natural log of secant theta, and you also have secant theta raised to an irrational power, can somehow give you 1. It's quite amazing that math can do this, that math even lends itself to problems like these being solvable, let alone reducing to something as clean as 1. I think it speaks to the harmony and connection that math is. But again, amazing problem. Thank you to the Daily Integral for all that they've done as well to make their website as refined and fine-tuned as well as it can be. I've really been enjoying my time on it, and I've learned a lot and improved as well as a problem solver because of it. So again, thank you to the Daily Integral. Make sure to go check them out if you haven't tried some problems for yourself. It's a great way to improve your integration and become more savvy with, I think, math in general. Just really pushing yourself and then getting that practice in is the best way to improve. Let me know if there are any other ways that you solve this problem, maybe a more elegant way, a more clever way, one that was maybe less tedious or less work, maybe even one that was more work. I think that if you can come up with an alternative solution to a problem in math, it just proves again and again that, math is an art form and not, just some procedure. So, yeah, let me know if you come up with anything like that, but again, thank you guys for watching. I really appreciate it, and yeah, keep integrating.